So again, welcome back. Today is all about L'Hopital's rule, but let's start out by taking a look at the quiz. And let me share my screen and we can play around with the quiz. Okay, so here's the question. We have a 400-meter track, and it's to be designed by having a rectangle with semicircles on each end. Okay, it's a standard track. I'm sure you've all seen it, maybe run around a track like that. I used to all the time. And the question is, find the dimensions that will make the area of the rectangle as large as possible. Okay, so I gave you a picture of the track because I know it's hard to do a picture on the screen, but I gave you a picture of the track. And you'll see we got this rectangle like this. And then on the other side of the rectangle, we have a little semicircle here, and we have a semicircle here. So what we're going to do is, in order to solve this problem, we got to see what's given. Well, one is we have a 400-meter track. All right, so 400 meters. So you see the word meters, and what kind of units is that? What does that tell you about the track? In kind of a geometry word? I don't see y'all jumping in. Yeah, it's a perimeter. So we're looking for the perimeter of this track, and it helps. And again, I can't put X's and Y's and all that, but I'm going to let the distance from here to here, this side distance on the rectangle, be X. And then since we have semicircle, I'm going to let R be the radius of the semicircle. That's standard. Okay, and they both have the same radii. So let's do the perimeter. Well, let's start with the easy part, and that is this guy and this guy are both X. So part of the perimeter is 2X. So let's write down perimeter equals 2X. I'll write down in a second. But then we also have to do around a semicircle. Well, the good news is you go around a semicircle over on the bottom and around a semicircle on the top, then you combine those two and you've gone around a circle. And how far is it around a circle of radius R? You're all supposed to know that from basic math. So if you have a radius R, how far is it around?
2 pi r?
Yeah, 2 pi r, because that's the circumference. So what we can do is we can say the perimeter, I'll just call that P, which was equal to, what was the perimeter? It's still in there. No. 400, because the 400-meter track is equal to 2X plus 2 times pi. Pi is over here, times R. Any questions so far? Okay, so we got the perimeter. Now what we're going to do is we're going to look at the area of the rectangle. So we have this rectangle. And how do we find the area of a rectangle? It's the base times the height. And what is the base and what is the height? Of this rectangle? Yeah, so the height is X and the base is 2 times the radius because it's a diameter. So our area is 2XR. Any questions so far? Okay, now we got to put these equations together. We want to find the largest area. So if we want to find the largest area, we have area is 2XR, and we only want to have one variable. We don't want to have two. So we can use the perimeter equation to get rid of one of the variables. And this is just asking to divide by 2, isn't it? So I'm going to take this perimeter equation, I'm going to divide by 2. I don't need the P equal anymore. 400 divided by 2 is 200. The 2's go away. And we have 200 equals x plus pi r. So in particular, x equals 200 minus pi r. And I can put that into my area formula. So my area right now is 2xr. And it's going to become 2 times 200 minus pi r times r. This way. So we can say my area is 2 times 200 minus pi r, and then times r. And so that's our area formula again. That came from, I don't know if you can still see it. That doesn't let me. Okay, that's okay. So it came from A equals 2xr. And it helps out now probably to simplify this a bit, multiply it everything through, because we're going to do some calculus and it's easier to do the basic algebra first. So I do that and I get 400r. And then minus, and we have 2 pi r squared. So I want to stop for a second. Any questions on getting to this point? Because I think this is the hard part, is getting to this point. We haven't done any calculus yet. Calculus is really easy, I think. Okay, we want to maximize the area, because that's what the question said. It said, find the dimensions that make the area as large as possible. So now it's time for calculus. What do you have to do to maximize area? So what's the step to maximize? Set not the area equals 0.
Take the derivative and set it to 0.
Yeah, we take the derivative and set the derivative equals 0. Okay, we're definitely not looking for when the area is 0. That would be r is 0, and clearly that's not a good track. Okay, it just wouldn't get you anywhere. So in particular, we're going to take the derivative, set it equals 0. So let's do that. Now for the calculus, and hopefully my promise was right, is that the calculus is the easy part. So if A is 400r minus 2r squared, what's A prime? What's the derivative?
400 minus 4 pi r.
Yep, 400 minus 4 pi r. And we set that equal to 0 because we're maximizing. Any questions so far? Okay, now it's pretty easy. We set it equal to 0, so I'm going to add 4 pi r to both sides and divide by 4 pi. And I get r is 400 divided by 4 pi, or 100 over pi. So let's write that out. Any questions? Okay. Now we want the dimensions, because that's what the question is. Remember, the last step is always to read the question. And I want to highlight the fact that we're looking for the dimensions, not the dimension. So we got r, now we got to get x, but that's easy because x was 200 minus pi r. So x will be 200 minus pi times 100 over pi. So let's write that down. 200 minus pi times 100 over pi, I believe, right? 100 over pi.
Yeah, it's pi, Larry.
Yep. I was just finding pi. You know, at the equation editor, always takes a moment to find everything. Okay, and that's easy. What do you get?
100.
100.
100. And now we got our dimensions. Any questions on that? Okay, and that's it. Do you agree that this is a really easy quiz to watch me do?
Definitely easy to watch you do than do.
Yeah, and that's why I don't know the secret, and I've never heard any instructor knowing the secret to teaching this stuff. Because again, I could do on the board, everyone smiles, they all get every step, no questions, no confusion, and then I give it to you guys, and it's really hard. And again, the only thing I can suggest is practice a lot of problems. That's the only way to get good at this is to practice. Okay, it's not to just watch me do it. That's not going to get you there. And
Yeah.
or maybe I'll look and you all got, you know, everyone got it right.
I did a sort of a different strategy than that. Same idea, but I just used a different equation. I went equivalating the circumference formula and the area formula in order to find r, which then gave me x, but not r. But it gave me the same x after I
Oh yeah, that
redid the
works.
equations.
Right. Yeah, there's two choices. Again, we're at the point where a equals, 200 equals x plus pi r. And you have a choice. You can solve for x or you can solve for r. I tend to like to do whatever's easiest. And I look at this equation, I say, you know, it's a lot easier to subtract pi r than subtract x and divide by pi and get a messy fraction. You should get the same answer though. But again, and that has to do with experience. Probably, again, I practiced a lot in my life. So I can look at this and say, you know what, I'm going to do the easy way, which is subtract pi x. Does that make sense? If you do it
Sure
the other way,
does.
it works. Yeah, the other way works, but it's not as easy, right?
Yeah,
Okay,
I didn't get to the end in the
okay,
time.
yeah, because it takes the time, yeah. And that's the thing is that and that's life too. If you go the difficult path, sometimes you don't get to the end, and then you don't finish what you're trying to do, not just in math, but in anything, right? And then someone who does kind of come up with a strategy to be most efficient, they're going to actually finish. And that's practice. That's all I can tell you. I look at this and I just say, it's so much easier to subtract pi r than it is to solve for r. And I go for easy. Any other questions? Okay, if there's no questions, let's get into new material and other questions. So first, any questions about anything in the course? And that could be, for example, your projects, your presentation projects that you're going to do, because that you should start thinking about now. And also, I want to make an announcement. What happens a week from today?
We have an exam.
Yep, exam 3 is a week from today. It's one of these weird ones. Usually when I teach this class, I do the exam in the week 11, but everything's changed now that we get the whole week of Thanksgiving off. I don't want to give an exam right after you've had a whole week off and forgotten everything. So that's why we're doing the exam the last day before our Thanksgiving week. And just note is after exam 3, we get a whole week off. We don't come back for another 10 days. So that's just a big note about the schedule that's coming up. So exam 3 is coming up, and I have now finished all the videos posting on YouTube, so you don't have to have Flash to open up the videos. And I have put in the link onto the syllabus. So I have it, It's a lot. This took me many hours. It's over, I think it's like 75 videos or something like that, of every kind of problem that you'll ever see, basically. Okay, and they're up there now. So now I'm working for next quarter, which I'm not teaching, but you'll have it in case you want to see it when you take Bruce's class. Are there problems that are going to relate to the videos on the exam? Yeah, I mean, it's not going to be exactly the same numbers or anything like that. But oh yeah, I've given you a video of every kind of problem that you ever see in this class. So there's a lot of videos. When I did this originally, you don't know how many months and months it took to make these videos happen. And they're pretty clean. They're pretty clean. My guess is the closed captioning may not be that clean because I let YouTube do it. But everything else should be really clean. So again, good idea to practice. Good practice problems, and you can watch the video. If you learn by video, that's a good way of doing it. Any questions before we move to L'Hopital's rule?
Larry, I have a question on the homework, but I'm not sure if we can go over that during office hours if you want to move on.
If it's a quick question, I can answer. If it's a long one, we should probably wait till office hours.
Yeah, I mean, it was the fence problem where we're supposed to put a ladder over the fence. And I got the equation to figure out the theta, but then I couldn't go any further. Like trying to get the derivative of the first, I just got lost. So
okay, I'd have to hear the question.
Okay. Do you want me to read it to you, or do you?
I don't have questions memorized, by the way.
Yeah.
Maybe read it pretty slowly, so I'll type in the important information as we go. So read it.
Okay, 1 second. I'm gonna bring it up.
Yeah, because they're randomized, so your question and someone else's will be slightly different.
Okay, I got it.
Uh-huh.
A fence 15 feet tall runs parallel to a tall building at a distance of 5 feet from the building, as shown in the diagram. And then
5.
And then it's asking, we wish to find the length of the shortest ladder that will reach from the ground over the fence to the wall of the building.
Okay, so we have a 15-foot tall fence parallel to the building. Okay, and building, and
5 feet from the building.
Do we want to go to the top of the building?
Just touch the building.
Want to touch the building? Okay. So the idea is we're going to have, and I think that this is really hard to do without a picture. So let me draw a picture. This is definitely one that you need a picture. Okay, yeah. So we got our fence. Okay, and you're going to know I'm not an artist. I'm not going to make it look like a fence. I'm going to draw a stick. Sound good?
Yep.
And then we're going to have our ladder. It's going to do something like that, right?
Mm-hmm.
And our building is over here.
Mm-hmm.
I'll just draw the building. Okay. Yep. And we go like that. Always a good idea to make it a right triangle. Do you agree?
Yes.
Okay. And then the fence was 15 feet tall?
Yes.
And it was 5 feet from the building?
Mm-hmm.
Okay, so 15. And 5 right there. Sound good?
Yep.
Okay. And our ladder is going to go from the ground to the building, right?
Correct.
And what we want to do is we want to find the shortest ladder. Is that the idea?
Yeah, but it's asking for theta.
Okay, so what angle should it be?
Right, yeah.
So let's write theta, okay. And I think it doesn't do Greek for me, so I'm just going to write theta. Can I write T? You okay with that?
I mean, I got the equation, I got the first derivative of that equation, but then it's asking to set it to 0 to optimize it, and that's when I just got lost because I have no idea what the
We'll
theta
get
would
there.
be to set that to 0.
We'll get there, but we got to set it up
Yeah.
to get it to work.
Yeah, yeah,
Okay.
yeah.
Okay, so that's what we've got, and we want to minimize the distance, right?
Yep.
From the ladder to the wall. So I'm
Mhm.
going to call that, how about H for hypotenuse? Sound good?
Yeah, that works.
Okay. Again, I don't know what you called it. I'm just trying to be as consistent as possible from what I've been doing. Oh no. Wait. That's a pain with Zoom. Okay, I'm in. Even gonna let me. I might have lost it. The save. Let's try doing this. It does this sometimes. The drawing doesn't always make it. All right, I think I got to start over. I hope I didn't lose the wall. Sorry about that, but Google does a weird thing with these guys. Did it save it? I hate that. I think it didn't save it. Oh well, but we got it in our minds, right?
Yeah.
Yeah, it happens sometimes. Sorry, but that's called
That's all right.
technology.
Yeah.
Technology does weird things. Okay, but what we can do is, again, we have the theta, right? And what we want to do is we want to find theta that minimizes h, right?
Mm-hmm.
Okay, so what we can do is we can, I got to draw it on paper. I can't do it without seeing it again. So let me get there. So theta, h, 15, 5. Got it. Okay, so the equations that we're going to get, if you want to do theta, is we're going to do some trig. And we have 5 and, so we have 15 and h and theta, right? Does that make sense?
Yeah.
Okay, so we have in particular, the opposite is 15, the hypotenuse is h. Is that clear?
Yep.
So we can say if you want the tangent of theta is 15 over h. Are you good with that?
Yeah.
Tangent, I'm calling it t, was 15 over h. Okay, any questions so far?
No.
Okay, and again, we know it has to go at least up to 5, right? Okay, does that make sense?
No, wait, what needs to go to 5?
The fence is 5 feet tall.
The fence is 15.
The fence is 15 feet tall.
Right.
Oh, it's 5 feet away. Sorry, I got the picture wrong. 5, 15. There we go. Okay, so the fence is 15. Yeah, so theta, yeah, 15 over h. That looks right. So in particular, h is equal to what? 15 times the cotangent of theta. Or t. Are you good with that?
Yeah.
Okay. And again, we've got all that. We got to use the 5, right? How do you use the 5?
Would it be or secant?
Well, the thing is, 5 isn't 5's not a side of a triangle.
Well, would it be 5 times secant? Because isn't it the base? Because we're trying to find if we know.
Right, we want to find the base, right? So the base is equal to, I just call it x plus 5.
Oh, right.
Does that make sense?
Yes.
So the base is equal to x plus 5. And that's kind of what we're going to have to use. And that's the problem. The cotangent may not work because we need to be in terms of the base, not in terms of the 15. Does that make sense? But we can use similar triangles. And we could say x is, do you see where the similar triangles are coming in?
Yeah.
Okay. And how do you use similar triangles here?
It would be x divided by 5 over the y, I guess, divided by x plus 5. Or no?
Okay. So y is going to be what? Where the building, the height, the building
the height
height.
of the building.
The height of the building. So if you're going to look at the height of the building is to x plus 5 or x plus 5.
Right.
Let's do it. There's an equation. Is to the height of the building. And how about y for height of the building? It's a vertical height. Is equal to x over 15.
Yes.
So we know that for sure, right?
Mm-hmm.
Okay. So that brings us to a relationship between x and y, and we need that. So we want everything in terms of x, right? Because we want to minimize x, right?
Mm-hmm.
Okay. We want x to be as small as possible, is what they said. Is that what they want?
I mean, eventually, yeah, because you have to figure out. I mean, they want the ladder to be as small as possible, but
Right. So if you want the ladder to be as small as possible, which is similar, okay. So what can we do?
I mean, would you divide by y to get what x? Or no, divide by x to get what y equals, and then plug it back in.
Yeah, if you want y will be 15 times x plus 5
So,
all over x.
Right.
I got to be careful about going too long because we do have to talk about today's stuff.
Yeah, no, I would say we can go into office hours. I don't mind.
Yeah.
We can put this off.
So once you get that, I think I might need to because I'm looking at the clock and we won't be able to get to what we got to get to today.
Yeah, no, this is a long problem. No worries.
Yeah. So
All right.
So I think I'll continue on at office hours. Sound good?
Yep. Thanks.
But I think I do want to get to L'Hopital's rule because I looked at my clock. It's like, oh. All right. So here comes the big thing. I'm gonna do it by something we did before. We're gonna have a much easier way of doing it. But there's some reasoning issues we'll talk about later. And that is that one, I think. If you wanted to limit as x goes to 0 of the sine of x over x. What happens when you plug in, by the way? What do you get? We don't get 0 when you plug in. Don't get does not exist either. So you gotta be careful with does not exist. Yeah, we get undetermined. We get 0 divided by 0. So if you plug in, you get 0 over 0, and that's really important. And that's going to be what we're doing today. That's what L'Hopital's rule is going to really be all about. And then there'll be variations on it. That's 0 divided by 0. And what is 0 divided by 0? For a limit, if you're taking a limit and you get 0 over 0, what does that mean? That means you've grown. It means you got to do work. And we did this one a long time ago in September. And we ended up with 1. And we did it using triangles and all kinds of things. I don't know if you remember, but that happened. Turns out there's a much easier way, kind of. So let me give you the big theorem. And the theorem is called L'Hopital's rule. And L'Hopital's rule says the following. And basically, it gives you what to do when you get 0 divided by 0. So let's suppose, or actually let f and g be differentiable functions. With f of 0 equals 0, g of 0 equals 0. Okay, so notice that our numerator, sine of x, if you plug in 0, you get 0. And x, if you plug in 0, you get 0. And we have the case where f and g are both 0 at 0. Okay, and actually maybe I shouldn't say 0. It doesn't have to be 0. It could be at some constant, at wherever you're taking the limit to. In our example, it's 0. Then let me write it this way. Copy and paste and adjust. The limit as x approaches c of f of x over g of x is equal to the limit as x goes to c of f prime of x over g prime of x. So this is a beautiful theorem, and beautiful meaning it saves you a whole lot of time. Okay, so again, one way of doing the example with sine of x over x is you draw a triangle and you remember some relationships on sequence of circles and all kinds of stuff. That's what we did, and do some limits. That was a lot of work. Okay, but we could think about L'Hopital's rules. Okay, is sine of x a differential function?
Yeah.
Yeah. How about f of x equals x? Is that differentiable?
I think so, but it's a flat line. So
Yeah, all polynomials are differentiable.
then yes.
Yeah. Remember, not differential means you can have something weird going on, like holes or asymptotes, that kind of stuff, or little V-looking things. Y equals x is beautiful. It's just a line. There's nothing better than that. Yeah, it's very differential. So what that means is that I can use the L'Hopital's rule, and I can say the limit as x goes to 0 of sine x over x now is equal to the limit as x goes to 0 Well, what's the derivative of the sine of x? You better all know.
Cosine x.
Cosine of x. And what's the derivative of x? Also easy.
1.
1. Was that hard, by the way? All right. Now I could try again. How do I, what's always the first thing you should do when you are trying to get a limit? It's always the first thing you do. You plug in. So now we have a new one. Let's plug in, and what do you get? So if we take the limit as x goes to 0, cosine x over x, you get cosine of 0 is 1. You get 1 over 1, and that's just 1, and I'm done. Isn't that beautiful? Okay, why didn't I do this when we first introduced the sine x over x? Do you remember? You know, why couldn't I have just done this? Yeah, you need to know derivatives, okay? And in particular, we need to know the derivative of sine of x. And to get the derivative of sine of x, actually, you need to know the limit as x goes to 0 sine x over x. So this is not a proof, what I just did, because it's circular reasoning. But it definitely is a quick, easy memory. If you forgot sine x over x, you can quickly use L'Hopital's rule. Okay, and this works, and we're done. Isn't that pretty? So what do you think? Do you think this is going to be an easier section or a harder section than the one that's due today?
Easier.
Yeah, I don't think I've ever had a student complain about L'Hopital's rule. Okay, so this is a beautiful, nice, relaxing day. Whereas the last one, I had very little to say, and it was brutal. Okay, so that's it. Let's do the proof, because that's my job. And I'm only going to do this proof. There's some other proofs that could come later in the class, but we're not going to do them. So the proof is the following. Well, we know that the derivative is, we know how the derivative is defined. So this is something you may not be thinking about. But when you want to show an equality, there are two choices. If you want to prove an equality is true, what are the two choices? In terms of techniques of proving, there's actually two choices always, because we need to prove this equal sign. Okay, for anything, nothing about limits, just in general. Any ideas? One choice is you start with the left-hand side, and then you show it's equal to the right-hand side. The other choice is you start with the right-hand side, and you show it's equal to the left-hand side. Do you all agree that that's the same thing? So this is one of those I'm going to start with the right-hand side, and we'll get to the left-hand side. So let's do it. So I'm going to copy and paste the right-hand side, and I need to arrive at the left-hand side. All right, so the idea here is this limit as x goes to c of f prime of x over g prime of x is equal to the limit as x goes to c. Well, let's see what f prime of x is. So f prime of x is the limit as, so x is, so we're looking at f prime, and we're going to look at f prime of x near c. And how does f prime of x work? Well, we can go, for example, x, we can go y approaches x. There are two ways of defining a derivative, and I'm going to do this way. And that was f of y minus f minus f of x over y minus x. Any questions on that? Okay, then I could do the same thing for g of x, for g prime. And that's the limit as y goes to x of g of y minus g of x over y minus x. And one nice thing about this is we were dividing two fractions. It's the same limit as y goes to x, so you can write it, think of it as a single limit. And when you divide two fractions, you can multiply by their reciprocals. You better all know that. So that's going to be the limit as x goes to c still. And now what we're going to have is we're going to have the limit as y goes to x. Let's do it this way. Of f of y minus f of x over g of y minus g of x. Because the y minus x's cancel. But now if x is going to c, then we can plug in, what is f of c? The hint is it's easy. It was the first part of L'Hopital's rule statement. What must it be to be able to use L'Hopital's rule? Let me scroll up a bit. What's f of c?
0.
Yeah, and g of c is also 0. So they go away. So the f of x goes away as x goes to c. The g of x also goes away as x goes to c. Now I can plug in y is going to x. So y becomes x. And I'm done. So it's a beautiful proof. That's all it is. You use the definition of the derivative, and then you cancel, plug in, and it works. Any questions on the proof? All right, so here's the wonderful thing. Okay, I'm going to give you the good news, and then I'm going to tell you the bad news, by the way. The good news is that L'Hopital's rule makes, I'd say 90% of the limits that you struggled with in the first couple weeks of class, easy. You want to hear the bad news? The bad news is, on the final exam, I'm going to tell you you have to use the definition. You're going to have to use the definition. No L'Hopital's rule allowed unless I tell you you're allowed. So just let you know, because I do want you to know how to do limits with algebra and stuff too. So this is a little dangerous to show you this. And I think it's why in older books they wait longer, because they don't want you to like forget everything you learned earlier. But you still need to know the old stuff, because it does come up for, there are some examples where you can't use L'Hopital's rule, but most of the time you can. Any questions? Any questions? Okay, let's do, again, but now we're going to just do lots of examples. So let's do some examples. Maybe I'll do examples. All right, so what if we have the limit as x approaches, and I'm gonna let c be infinity, which you're allowed to do actually. Let's say x approaches infinity of e to the x over x squared. Any questions on the question? Okay, what's the first step? Yeah, plug in. What do you get when you plug in? Infinity over infinity. So now what I'm going to do is I'm just going to tell you that we can change this f of c equals g of c equals 0. And I can write or f of c equals g of c equals infinity. So it turns out with L'Hopital's rule, if you had either of those, then you can still use it. So if you have 0 over 0 or infinity over infinity, L'Hopital's rule is allowed and it works. I could prove it for you, but what I try to do is I try to only prove one thing a lecture. Otherwise, pretty much that's all I do in class is just proof. So you could look at the book and see proof of that and go online, whatever. But you can trust me, or you could ask an office hours, I'll prove it for you. But it is very provable. So when you get infinity over infinity, you can still use L'Hopital's rule. And that's a big deal. So what we get here is infinity over infinity, which means I can use L'Hopital's rule. And I can take the derivative of e to the x. What's the derivative of e to the x? You better all know.
E to the x.
E to the x. How about, and then we take it divided by the derivative of x squared. What's the derivative of x squared?
2x.
Yeah, 2x. Again, derivatives aren't going to be that hard. And what should you do after you use L'Hopital's rule? What's the next step? Yeah, we plug in. And what happens when you plug in? So what happens when you plug in? You'll get infinity over infinity. So I want to tell you kind of a good rule of thumb for doing these kind of problems. Yes, we get infinity over infinity, but we look at it and decide whether we've made it nicer or have we made it no better or worse. So if you look at the numerator is exactly the same. The denominator is a line instead of a parabola. Lines are simpler than parabolas. Do you agree? So that means we've made progress. And if you've made progress, then you keep going. Whereas if it got worse, then L'Hopital's rule is probably not going to work. But this one actually got better. Okay, the 2 and the 2x is no big deal. You can pull that outside if you felt like it. So I can use L'Hopital's rule again, cross my fingers and see if this is going to work. So what I can do is do it again. Derivative of e to the x again is e to the x. What's the derivative of 2x? Yeah, derivative of 2x is 2. So what do you do always after L'Hopital's rule? So what's the next thing? We plug in. And what do you get when you plug in now? Yeah, we get infinity over 2. And by the way, half of infinity is still infinity. So you get infinity. Okay, and that's it. We're done. We found a limit. The limit is it does not exist. It's infinity. Infinity is a little more informative than does not exist. Any questions on this example? Any questions? All right. By the way, if this was x to the 10th, you'd have to use L'Hopital's rule 10 times, and you'll eventually get it. And you could actually prove that e to the x over any polynomial always goes to infinity as x goes to infinity, using L'Hopital's rule n times, where n is the degree of the polynomial. All right, now comes an application problem example. Let's see, can any of you remember what is the formula for compound interest? Any remember? If it's compounded, say monthly, it's definitely not that. It's not an exponential. It's not e to the something. So that might be compounded monthly or quarterly or daily or yearly or, you remember? Okay, if you don't remember, let me type it out. And that is that P, put it as equation form. Oops, capital P. Is it P? No, sorry, A is what I want, is equal to P. Amount equals a principal times, and then the formula was 1 plus r over n to the nt. And remember that. Does that ring a bell, at least to some of you? It's a really important formula. Comes up a lot. Okay, in all kinds of places. Okay, in economics and biology too, because if you're looking at a species that reproduces maybe every spring, then you can. It's basically the same idea. It's not money interest, but it's how many in the species there are. All right, so now the question is, what about continuous compound interest? Okay, and we got one in the chat box, which remembered it, PE to the RT, but why is it that true? Okay, again, you're thinking it's PE to the RT, but why do you think it's PE to the RT? And not because your teacher told you it was, because continuous compound interest is the following. What happens when n approaches infinity? Because that's what continuous compound interest means. It means the number of compounds per year becomes infinite. So another way of saying that is, what is the limit as n approaches infinity of p times 1 plus r over n to the nt? Any questions on why this is what gives you continuous compound interest as a definition? All right, well, as you're used to, if you want to take a limit, what's the first step? We plug in, and if you plug in, we get P times 1 plus r over infinity. Anything over infinity is just 0, so we just get 1. But it's 1 to the nt, n goes to infinity, so it's 1 to the infinity. What is 1 to the infinity? What's 1 to the infinity? Okay, it's tricky. Okay, and we're talking about, these are limits. Whenever you have infinity, that means you're talking limits. So notice that this is 1 plus something that goes to 0, which goes to 1, but it's a little bigger than 1. So we got a number that's a little bigger than 1. And if you take a number that's a little bigger than 1 to the infinity, you get infinity. Is that clear? Do you all agree? On the other hand, if we think of this as 1, 1 to any power is 1. So is it infinity or is it 1? And that's a tough question. And whenever you get two answers doing algebra, then you know there's some issue. And that's why this is a undetermined. This is a do algebra, or in our case, we're going to do algebra and L'Hopital's rule. Any questions on the idea of this? All right, so here is the trick. I am going to take a log of both sides. And I can put the log's a continuous function, so it can get put through the limit. So I'm going to take the natural log of both sides. And by the way, the natural log of p times something is the natural log of p plus the natural log of the something. Natural log of p doesn't have an n, so I can actually pull that out and write this as ln of p plus the limit as n goes to infinity of ln of 1 plus r over n to the nt. Are y'all okay with that so far? That's a log rule. Now, what happens when you have a log of something to a power? What can you do? Looking for another log rule? Yeah, power goes out in front. So I can take that nt and put that out in front. Now it's got an n in it, so you can't put it on the other side of the limit, but you can still write nt times ln of 1 plus r over n. Any questions so far? So we're getting there. All right, here's the next thing is, now that we've done some algebra, what should we do? What do you do after you do algebra? When you do limits? Plug in. So if we plug in, we get infinity, nt becomes infinity, then goes to infinity, times ln of 1. So what's infinity times 0? Because log of 1 is 0. Any ideas? Okay, 0 is one idea, because anything times 0 is 0, except this is actually slightly bigger than 0, because we're doing 1 plus something, even though it goes to 0. And if you have something slightly bigger than 0 and you multiply by infinity, you get infinity. So there's another problem. So infinity times 0 is another problem issue. Okay, it means that it's undetermined. We need to do more work. So what I'm going to do is I'm going to do more work, more trickery. So what I'm going to do is I'm going to take this nt and I'm going to bring it. I want to use L'Hopital's rule. Okay, I know that because today's L'Hopital's rule day. So what I'm going to do is I am going to bring it as a fraction. And I'm going to say this is the same thing as ln of 1 plus r over n over, if it lets me do it, there we go, over 1 over nt. Any questions on this trick? Okay, again, knowing to do it is the hard part. Doing it's not hard, but knowing to do it is really hard. And this works. And the reason why this works is now we can plug in, and if n goes to infinity, the numerator goes to 0, and the denominator also goes to 0. Do you all agree? So we get is 0 over 0. And if you see 0 over 0, what do we do? Hint, think French. Yeah, now we use L'Hopital's rule because we got 0 over 0. So we take derivatives. So now we got to take the derivative of the natural log of 1 plus r over n, and n is our variable, by the way. R is a constant. So that's the chain rule. The derivative of 1 plus r over n is negative r over n squared. So let's write this out. So we have negative r over n squared. And then we have a log, and the derivative of the log is the 1 over function. So that's times 1 over 1 plus r over n. I think I can write as r over n that way. Otherwise, it gets way too small. And in fact, let's do the following. Make this bigger. Okay, then we take the derivative of 1 over nt. So that's nt to the negative first power. That's also chain rule. That's going to be negative t times nt to the negative second, or we could say, let's write this way. So we're going to have nt, and then over nt squared with a negative sign. So n squared t squared. Sorry, it's going to be n, not nt. It's going to be t over n squared t squared. And there'll be a negative. Any questions on the calculus? Why is this good? Okay, take a look at it. It simplifies. That's why it's good. So this is equal to, let's write down what it's equal. So the n squares cancel. So the r over n squared just becomes an r. And this n squared goes away. The negatives go away. I lost my ln of p. And it's already too long. So next line. So those went away. The negative t over t squared That's 1 over, the t over t squared is 1 over t. Is that clear? And 1 over t is t. So that becomes RT. I can put that over 1 if I want. So any questions on all the simplification I just did? Okay. So now I can plug in. What happens when n goes to infinity? I know it's a lot of algebra, but what happens when n goes to infinity? What's r over infinity? Hopefully I haven't lost y'all. Yeah, r over infinity is 0, so we got 1 over 1 plus 0. 1 over 1 plus 0 is 1. So that 1 just goes away, and we're just left with RT. And we still have the log of p. We're almost there. All right, so what we get, let me just summarize what we've got. On the left-hand side, we have ln of a. On the right-hand side, we have ln of p. And then plus RT. Okay, now again, we did a trick and we found the log, but we don't want a log of a, we want a. So to get rid of the log, we exponentiate both sides of base e. So now we can go ahead and say that a is equal to e to the ln of p plus RT. But that's actually quite nice because that's equal by exponent rules, e to the ln of p times e to the RT. But what's e to the ln of p? Yeah, p. So we get p e to the RT. Okay, and you might have even heard this as the Peird equation. Okay, this is a very famous equation, a equals pe to the RT. Okay, and this is the proof that it works. My guess is you've seen it before more than once, but you've never seen the proof. Am I right? Until now. And the reason why you've never seen it is if you don't have L'Hopital's rule, good luck. So this is a major equation that relates compound interest that is not continuous to compound interest that's continuous. Any questions at all on this big result? This comes up in every subject, every STEM subject at least, and economics, which isn't STEM. Any questions? Okay, we still have a little more time, so let's do some more examples. What if we had the limit, which is what today's all about, by the way, so shouldn't be surprised by me saying limit. And how about as x goes to 1, of the following: 1 over x squared minus 1, and then minus 1 over ln of x. Any questions so far? All right. So what's the first step? And I'll even do it, we need to do it this way or it doesn't make any sense. So let me go from the left. Because you can't go from, you don't want to go from the right, trust me. Because you don't want negative, we just don't want to do that. We could do left, but, or right, but just go from the right. So what's up? What do you get? When you, what's always the first step? You better all know. Yeah, you plug in, and what do you get when you plug in? So you plug in, this isn't that hard. Doesn't need calculus even. Not quite does not exist. We get 1 over 0, okay? And x goes from the right, so it's positive 0. So everything's positive. So that 1 over 0 is infinity. Minus, well, natural log of 0, a natural log of 1 is also 0. So that's minus 0, minus infinity. What's infinity minus infinity? Okay, again, different answers, which is what you're supposed to give me. The answer is undetermined, because it all depends on which infinity is bigger. I know that feels weird, but infinity, there's bigger infinities and smaller infinities. So this is an undetermined one. So we can't just plug in, that does not work. So what we can do is we can do algebra. It's your favorite thing in the world, isn't it? So how do we do algebra? How do you subtract two fractions? Common denominator, good. So we do algebra, common denominator time. So I'm going to have a 1 over x squared minus 1 times ln of x, because that's the common denominator. When there's nothing special about the two, then common denominator is just multiply them. And the numerator is going to be ln of x times x squared minus 1. Any questions on what I've done so far? What's the next step? Oh, do you know what? It's not time, sorry. It's ln of x minus. Okay, and then we plug in. Okay, so if you plug in, the numerator is ln of 1, which is 0, minus 1 minus 1, so it's 0 minus 0, and that's 0. The denominator is going to be 0, so it's going to be 1 squared minus 1 is 0 times ln of 1 is 0. That's another 0, so 0 over 0. If you get 0 over 0, what do we do? Yeah, new rule, L'Hopital's rule. It's actually not new at all. It's hundreds of years old, but I'll let you have new. It's new to you. Okay, so we're going to use L'Hopital's rule. So let's do that. So derivative of ln of x is 1 over x. Derivative of x squared minus 1 is 2x. And then I got to take the derivative of x squared minus 1 times ln of x. I need the product rule for that. So I'm going to have The derivative of x squared minus 1 is 2x. And then plus x squared minus 1 over x. Any questions on this step? Any questions? Okay, so we're getting there. At this point, probably a good idea to multiply by x, get rid of the messy fractions, if you're okay with that. So I'm going to multiply by x. And when I do that, this x squared minus 1 over x just becomes x squared minus 1. We're going to have a 2x squared ln of x. The 1 over x becomes 1. And then minus 2x squared. Any questions on the algebra there? That minus 1 is not supposed to be up at the top. That's better. Okay, what's the next step? Yeah, plug in, and I like to say, plug in and cross your fingers and hope you actually get something nice. So if we plug in, we're going to plug in 1. We get 1 minus 2. That's 1. That's negative 1. And if we plug in 1 here, we get 2 times 1 times ln of 1. ln of 1 is 0, so that's 0. Then you get plus 1 minus 1, and that gives you a 0. So what's the answer? Negative infinity, or probably does not exist, is even better. You can go and try and see if it's positive or negative infinity, but DNE is better. Because I don't want to look at that denominator and try and figure out if it's positive or negative. Okay. So DNE. So this limit does not exist. And you never know what you're going to get until you do all the work. Any questions on that? Okay, I think I have time for one more quick example. So what if the limit as x approaches 0 of x to the x power? It's always a fun one. So if you plug in, you get 0 to the 0. Well, 0 to anything is 0, but anything to the 0 is 1. So I like to think of it as a tug of war and nobody wins. Therefore, it is undetermined. We need to do work. Any questions on that? But what we can do is we can rewrite this. Is we can write the limit as x goes to 0, and I could take ln of x to the x, and ln of x to the ln of e, sorry, it's e, I could take ln of both. So I'm going to call this y. Let's write it this way, equals that limit. And what I can do is I can take ln of both the sides. And I could say ln of y is equal to ln of the limit, which is the limit of s to the x, which is equal to x times ln of x. But that, we've kind of seen this trick before, and today is all about algebra tricks, is equal to x over 1 over x. And now when we plug in 0, you get infinity over infinity. So that means we can take L'Hopital's rule. And that's the whole point. So let's do L'Hopital's rule. So we can take still limit as x goes to 0. Ln of x is 1 over x. And then the derivative of 1 over x is negative 1 over x squared. And we can do some algebra. And we can call that negative x squared over x, which is negative x. And if we plug in 0 to negative x, you get negative 0, you get 0. So if ln of y is equal to 0, what is y? Y? Then we call it a day. 1. And there's our limit. Okay, a lot of little algebra tricks, but I think it's easier than word problems. There aren't a lot of word problems. There's lots of algebra tricks, though. Okay, there are a lot of applications of L'Hopital's rule. I showed you the economics one, but so I am going to stop my share and call it a day. I'm going to hit stop recording.